All right, so we'll start with a few news items, another 5 minutes anyway. So we now got 28 people sick with the coronavirus in San Francisco, which is why I imagine I do not expect college to resume face-to-face classes in 2 weeks. For some reason, they have put off that decision for a while in the bizarre hope, I suppose, that things will be better in 2 weeks, but I don't think that's going to be the case. And now all the bars with a capacity over 100 have been ordered to close. So for 7 weeks. So I would assume it'll be the same for the college. And Trump has now banned travel from Europe and the UK and Ireland. And apparently they're considering domestic travel restrictions too. Now I got classes in a month or two. I was supposed to be teaching in Indiana and Illinois, and it sounds like I might have trouble getting there. This was interesting. This guy used to be a city college trustee, and there are many, many clues that our trustees are crooks, and this guy here got caught at $420,000 in check fraud. He took a city agency called DBI, and he just modified the checks by putting letters before and after the name of the city agency to make it so he could put it in his private account. Very obvious and simple forgery to the tune of about $500,000. When I was in Illinois about 20 years ago as a student in Chicago, the person in charge of the alumni fund was just writing checks straight out of the alumni fund to like prostitutes and buy cars and stuff for years before they noticed and caught him. Colleges have very weak oversight, so the very simplest kind of crime tends to run rampant. I've been hearing ads from these guys, and I would love to get some kind of free trial or something and see if this works. This is supposedly homomorphic encryption. Homomorphic encryption sounds like science fiction. You encrypt data, and then you search and use it without ever decrypting it at all. So you use some kind of encryption that preserves some kind of pattern in the encrypted data. And I think the idea is for simple things like credit card numbers or social security numbers, you could still somehow do a search to see if a credit card number is in a list without ever decrypting anything. And the idea is, as I understand it, that you will now be protected even against attacks like RAM scrapers that are stealing the RAM from the machine because the data is never decrypted at all. This has been introduced by mathematicians quite a while ago, but all the implementations I've heard of have been extremely slow to where they're completely impractical. This is the first product I've heard that claims they can actually do it in some practical way. So it really would be nice to see what this can do and how fast it is. Anyway, a lot of people have been talking about this. You can, when you have a new disease, you can do what was done centuries ago, even though you don't know what you're doing. You just take some blood out of a person who has had the disease and put it in a person who hasn't had the disease. That's called, I think, inoculation instead of vaccination, but it's somewhat effective. And they've been using it in China, and people are talking about using it here. It does sound like a pretty good idea, I would think. So this woman and her team cracked the largest RSA key, which was 768 bits. So there's a whole series of these challenges that have been up for like 50 years. And anyway, so the largest thing that's ever been cracked without knowledge of the key is 768 bits. So people that are using 2048 or more are presumably safe for a while, but that's why those challenges are there. And this judge resigned with a very nice, clear letter explaining how the court is now implementing right-wing strategies. And this is something that happened about 100 years ago. There was and he says they are legislating from the bench, exceeding the Constitution and so on. It's interesting to see. Whole Foods has workers sharing their sick time so that they can trade it. The people who are healthy can give it to those who are sick. They do the same thing at City College. Motherboard is angry. Why don't they just give everybody more sick time? But anyway, that kind of flexibility is useful. I'm sure there are people who just like them to give it away anyway. We'll see what happens. And this was, I thought, kind of hilarious. Jack Ma, I was waiting for this in a way. Jack Ma is the head of Alibaba, and he is now going to donate 1 million masks to America, and I think 1 million test kits or something. So masks and test kits and such, which is nice. It is, I think, good PR for China that they are so far ahead of the United States on this. Of course, everybody seems to be ahead of the United States except Italy, and it may possibly have an effect on the next election if Trump's supporters ever come to realize that he just doesn't care about them at all, and that people are just numbers to him. But they don't seem anxious to admit that. And so maybe the Pentagon is going to send the Jedi to Amazon instead of Microsoft. They really are going to reconsider part of it, so we will see what comes of that. It'll make a big difference in the cloud security space. All right, so we're up to the official time, and I'm going to pursue, well, we had one person who then left. If there's only one person here, I'm thinking perhaps it's not worth doing this. Maybe I'll just put off this lecture till next week. Let me point out the hands-on project I recommend, though. You should start doing them. I just got them working. If you go to 127, you'll see down here the Windows project starts. And so you can make a Windows Server virtual machine locally or a machine in the cloud. And then you can do this exploiting vulnerable server on Windows. And I guess I won't demonstrate it until next week because people seem not to be showing up. But let me point out what you do here. This is the most important project in the whole course from students who told me they went off to get the OSCP. This is where you go through all the steps to take over Windows machine. You fuzz it, you find the vulnerable software, you develop the attack, and when you're done, you get up with an interpreter shell on the machine, and then I have a cloud server, so you can practice a remote server. I tested this morning, and it's all working. So this is very good practice for real exploitation, for real pen testers. So take a look at that, and I will demonstrate it next week. But I think I'm not going to do it this week if only one person shows up. Ah, Deborah made it. Well, maybe I'll continue. Alex and Deborah, I think you people will count. Let me, it's very hard. Let me wait till 10 after. I'm going to pause the recording. And let me wait till maybe 10 after and see how many students we get. Okay, we got enough people, so we will proceed. So let me find the slides. Let's start with information about Windows, and then I want to demonstrate an important project. So we will carry on. Why is my page up key not working? I'm hitting the wrong key. That'll do it. All right, so make this big. All right, so here's what we're going to do. We're going to talk about how Windows software works, and there's a lot more about this in the malware analysis course, which is coming around next semester, presumably, although who knows what's going on next semester. Anyway, so we'll start with the basics of how Windows software works. You have, good. All right, now when you write Windows software, you don't write everything from scratch. You have Windows API is code that Microsoft gives you to use. And the same thing's true if you make a game on Facebook or something. You have an environment, and the person who designed the environment gives you functions to use. And all you do is call those functions. So that's called the Application Programming Interface. In Linux, you use syscalls, and in Windows, you use the API. And this is a set of dynamic link libraries, DLLs, and they change with each version of Windows and each service pack. At least the address has changed, but most of the function calls remain the same. So if you look in Microsoft websites, there are documentations of all these. So here is the command that creates a window. This will create a window, and the reason it has an EX at the end is there was once an earlier version called create window, and then Microsoft extended it here. And so you have a handle to the window here, which is the output of this function. It creates a window, and then in here you have parameters like the title of the window, and the width and height of the window and other things like that. So you can call this API function, and it'll call the function into DLL, and it will then open a window for you. And if you want to open a network connection or take keyboard input or anything you want to do, pretty much, you call an API to do it for you. So all the programmer is doing is just call a series of calls to the Windows API. So these are all using DLL files that Microsoft has precompiled, and you can see the loaded DLLs with Process Explorer. If you run Process Explorer, then you can see here, here are all the DLLs used by a process, and I think this is SVC host here that I'm looking at. And you see, it'll show you all the DLLs that it's using. A typical program is using many DLLs, and each DLL has many functions, and it's using many functions in there. So these things are called portable executable files. That is the generic term for Microsoft executable format. In Linux, the equivalent is elf. And this contains a header which lists all the required DILs so that when it launches, it can quickly connect to all those DILs. The ones that are already in memory, it will just connect to. The ones that are not in memory, it will load. And if it can't find one of them, it will pop up an error message and say, I need this DIL, where is it? So this is in the header. If you open this, use the program called PE View, you can see the header of a DIL file, and there are sections of the file. The text file contains the executable machine language instructions, and the resource section contains icons, and there are other sections of which are not always there, but are often there, like data and relocation. And there's an import table, and the import table is here telling it all the DILs it needs to load. So this is Notepad, and you see it's loading kernel32.dil and advanced API.dil and a graphic data interface and other ones here, user32 for user interaction, and so on. So here's common sections. Text is instructions to execute. Data is global variables. iData is import descriptors, resources, and relocation data we're going to talk more about later to relocate the entire program in memory. So a DIL has a base address. A library is intended to load at a certain address, but since the libraries are all written at different times by different people, you could have two libraries that try to load at the same base address, and you can't have more than one program loaded at an address. So if that happens, one of them has to be moved, and that's called rebasing, and that uses the relocation section. So you need that relocation section in order to make it possible for your DIL to be rebased. So I've got some Kahoots, and we will got enough people to do some version of this, so we shall. If nobody else shows up, you're all likely to win, I would say, but that's an acceptable consequence, I think. To few the proud. Aha, there we go. Not officially in class. Well, anybody's welcome. Well, I'll give it another 10 seconds, see if the third person is coming. Let's see if there's any chat message. I can't play, doing laundry. Okay, good. Only 2 people. Well, we'll carry on anyway. People can look at these later to review questions anyway. All right. So, what section of the PE file does rebasing? All right, that's the relocation section. All right. What section contains machine code instructions? All right, text is right. All right. And what term is the set of functions Microsoft provides? Okay, that's the API. Everybody got it wrong. Yeah, the DILs are the files that hold it, but the API is the set of functions. They're related, but the API is the better answer. All right. And what's the overall format for all Windows executable files? Okay, some of them are EXEs and some are DILs, but they're all PEs. PE is the container that includes all Microsoft executable formats. All right. And where's the precompiled library code? Okay, it's in the libraries, DILs, not in those other places, although it's technically a PE file. It's a DIL file if it's precompiled library code. All right. And where are the icons? All right, in the resource section, fair enough. All right, well, Alex J is the only one that appears to have a identity to record. I'm going to put it here. I've got two screens today, so you won't see it, but anyway, Alex J. All right. All right, so let's carry on. So then we got imports and exports. Imports are if your program calls libraries, then it imports handles from those libraries and it calls them off. DILs, executable files use DILs almost all the time, and DILs often use other DILs. Exports, so DILs have many exports, EXEs typically don't. EXEs typically only have one entry point, and they don't export other entry points. So here's the imports of Notepad. Notepad uses many functions. It uses open process, registry, close key, event unregister, create status window, and so on. And you can see there's a scroll bar, there's a lot more. These are all the functions used by Notepad in different DIL files. And here's the Advanced API 32 library exports. These are all the functions it exports, and you can see there are a lot of them. This is just the beginning of the A's. So this library has abort system shutdown and access check and add ACE and many, many, many things in here, all to do with the API, advanced API. So anyway, all right. When you load it, it tries to looks in the header and sees it needs a DIL, and you will often hit DIL hell where it needs some weird DIL that it can't find. So the point of this is you could write software, then you could rely upon one exact DIL version, and then later on, Microsoft might change that DIL so your software doesn't work anymore. So you could package the DIL with your software, and it will load that DIL from the local directory, which would be different than loading the system DIL, and that way code written for old versions of Windows might be more likely to run on modern versions of Windows. It sounds good, but in practice, often the result is the program gets confused about where to find the DILs and it loads the wrong DIL or it can't find it. And then you have version conflicts and this error popping up. This was also used by the United States against Iran in Stuxnet. You would put on a thumb drive a file and then a DIL, and if drawing this window that displayed the contents would run that DIL from here, and that would take over the machine. So just looking on the stick to see what was on there was enough to make you owned, and that's how we attacked the Iranian nuclear isotope separators. Every executable believes it is at the same memory address. It thinks it's at 400,000 hexadecimal, but that's of course not possible. What's really going on, that's a virtual address, like a virtual machine. Each executable is running with an offset. So for example, you might have one EXE running at 300,000 and one running at 500,000, process A and process B. They'll both run fine, but they're both mapped. So they both think they're running at 400,000. There's a mapping table that keeps track of where they really are. One process can typically not reach into another process's memory, so it doesn't matter that they both have the same virtual address. All right, and so if you load anything in a debugger like Ollie debug, you'll see the code starting near 400,000 all the time, because every program believes that's where it is. And the debugger shows you the relative address, the internal address. Now, heaps are used for temporary data storage. If you store something and you process it and then you're done and you want to free that memory to store more data later, and so you use malloc to allocate a chunk of memory and then free to deallocate it and make it available for reuse. Linux typically uses one heap. Windows has many heaps and they're really quite complicated. So heap corruption attacks on Windows are more complicated than on Linux, but they still work. Windows is a multi-processing system. You can launch multiple applications at the same time. Those are processes. Each process is divided into threads, and threads are what gets its unit of processor time. And this means if you run a process like Microsoft Word and you start, say, printing something, then you can also make a new document and edit that while you're printing, because they'll run in different threads or something like that. I haven't looked specifically for that example, but that's the idea. You can have one program with several different things going on, each of which moves forward. All right. Anyway, so this is the plan is if something slow happens, like you're waiting for user input or network data, then that one thread will be waiting, but other threads might move forward. So something can still be happening while you're waiting. You can see them in Task Manager. So if you view a process here, you'll see this machine has 41 processes, each, and that's a total of 677 threads and 18,000 handles. Handles are what you saw at the beginning, a handle pointing to an open window, pointing to an object that you're referencing. So each process has many threads and each thread has many handles. All right, those are pointers to objects like open files or other things that you're using. And here again, you can get the entire property. So there's explorer.exe, and if you use Process Explorer, you can see the threads, how many threads there are, and you can see there's quite a few, looks like 15 or so, and there's a scroll bar, there's even more. Process Explorer will let you see all the threads if you need to go into that level of detail, which you normally don't need to, but it is available if you want to really find out what's going on in a program. So let's try another Kahoot. Leave page and 6B. All right. All right. Low population today, I imagine some people might possibly be distracted by other events. All right. All right. So which memory section is a single block in Linux, but many pieces in Windows? That's the heap. All right. All right. And which item has the largest number of instances? Handles. You have a few windows. Each window has a process which has many threads, and each thread has many handles. Handles is the most numerous thing. All right. What is the allocation unit for CPU time? It is threads. Each thread gets some CPU cycles, then it strobes to the next thread and the next thread, and that's what's called multiprocessing, or not multiprocessing, but multitasking. There, okay. All right. Good. And what part of a DIL lists the entry points that it provides? Those are the exports. So if I'm a library and I offer 100 function, I export 100 values you can use to enter. You can enter this at 100 different places to get different results. All right, good. I'll just keep updating the score, although it is a trivial exercise today. And we've got the last section of this, and then we'll get to the hands-on, which I think is probably the most fun. But this is kind of amazing. This is how Microsoft became so important and valuable and also so insecure. The DCOM model and the DCRPC, remote procedure calls, and distributed common object and distributed computing environment. What Microsoft, like Facebook, is trying to make a platform so people can make money. And Bill Gates was, in the early days of computing, a lot of people were just hobbyists and open source people, and they were not thinking about a business level at all. They were just loving the machines and making it work. And Bill Gates, even as a teenager, was the first guy that got mad when people copied his software and wanted to copyright it and charge money for it and get a business going. He had far more business awareness than most computer enthusiasts at the time. And so Microsoft was shamelessly commercial right from the start. They're trying to build a commercial operating system that you can use to make software and sell it. So the point here is you should be able to write code, and then you should be able to sell your code to other companies to repackage into their code, reusing code. And that's what happens here. You make component object model modules, and then you can tie them together with Visual Basic. Just like I said, most programs, or I think essentially all programs on Windows, are just calling functions in DILs. You can sell your own DIL with more libraries, which people will just plug in to their code. So you write COM objects in any language you want, and then you have to include an interface descriptor language file, which explains how to use it. So here's an IDL file of how you're going to use something, and it just shows you this is a function, and it's got a string here and something called type1 here, a long element, a context handle. This is the technical specification of how you feed all the data in to use it, and it starts with this UUID, which is the universally unique identifier of this object. So you can purchase this DIL from somebody or write it, and the IDL tells you exactly how to use it, just like the API documentation for the Windows API tells you how to use those functions. So this specifies the arguments and return values and the GUID, and that's how you call any object that you get. So there's two ways to load a COM object. You can load it directly as a DIL into the process space, and then applications on that machine can use it. You can launch it as a service, and then it will launch and run independently, and other processes on the machine can use it. Running as a service is more stable and secure, but much slower, 1,000 times slower. And the service control manager shows these services running in the background, and there are something like 50 or 80 services that are running in the background of a normal Windows machine. And then Microsoft wanted to make it easy for you to write software that would be used more widely. So what you can do is you can make a simple change to tell your program to load a function from a different process or even a different machine. So you can not only publish your function to other processes on the same machine by making it a service, you can connect it to a network socket and distribute it over the LAN or even the internet. So that is the remote procedure call. And that's run by the remote procedure call endpoint mapper listening on port 135. And when you connect to port 135, it will have these DCE, RPC, and EPM packets going back and forth, where you ask the server, what are you offering for remote procedure calls? And it gives you a whole list of them. And then it tells you, here's a UUID offering something, here's another UUID. These are like the floors in a building. So there are 5 floors available, and here's different things you could connect to. So it is like a multi-use interface to share many functions over the network. And it turns out to be extremely important. If you go into services and look at remote procedure call, you will find the DCOM service process launcher and the RPC endpoint mapper, and many, many functions of Windows depend on these things. If you were to turn this off, a whole bunch of Windows would not work anymore. All right, the problem is the logic flow here leads to security problems. You wrote code to be a subroutine for just one function. Then somebody else in your company decided to publish it for other functions, processes on the same machine. And then somebody else decided to just connect it to the network socket and share it with everybody. So often you have a problem, just like when companies go to the cloud. They have a server in their own custom server farm protected by firewalls and such, and then they put it in the cloud, unlike Amazon Cloud, wide open to the world, without realizing that they have to be more careful about security when they expose it on a wider stage. And many, many viruses and vulnerabilities came through RPCs for this problem. So there are hacking tools like Recon, DC, Spike, and other tools that will just try to probe these RCEs and see if they have vulnerable services, which they very, very many times have had. All right, when you're running a process, there is a token. You can see them in Process Explorer again. So here's the explorer.exe, and here's the token. It's running as Sam. So Sam is logged in, launched this, and this is the object address that tells you the token. The token specifies who is running a process and therefore what privileges it has. Unfortunately, you can create new threads and you can copy any available token to them. So if there is a high privilege process running on the machine, like something running with administrator or domain administrator permissions, you can copy the token from that and then elevate your own process up. It's one common way to do it. And then there are exceptions. When you have some kind of illegal instruction in code, some systems like Cisco routers will just reboot the whole system and throw away everything, abandon all processes. Now that's not acceptable for an end user device. What you would rather do is terminate just one process and provide a helpful error message. So if you try to do any of these things, divide by zero, execute non-executable memory, or go to an invalid memory location, which means jump to a memory location which is not reserved for use by your process and is therefore not available, then you get an exception. The processor sends an exception, like an interrupt, saying something bad has happened, and your program has a chance to handle it. That's the first chance. You can write an exception handler in your program, and the more professional programmers do, of course, and then when something goes wrong, your program continues to run, and it pops up a box that you wrote that tells the user, oh, something went wrong, click here to contact our help desk or something. But if your program doesn't handle it, it goes to the operating system, and the operating system will either pop up a box like Professor Watson or something, or it will die with the blue screen of death. So that's the, if it's a kernel exception and it can't recover from it. So you can see it in Immunity Debugger. If you're debugging a process, you can see the structured exception handler chain. And this is just a chain of addresses that have code put in the application. So it will try to, this will try to handle the exception, and that will try to handle the exception. And if all of them fail, then it will just go to some default operating system handling, which will either pop up, and if it's a user land process, it'll pop up an error message and stop the program. If it's a kernel exception, you get the blue screen of death. All right, so if you can, the SEH is just sitting in memory, like the stack and everything else. So sometimes you're able to overrun something and hit the SEH chain. So this is a place you can, if you change these addresses, then if you cause an exception, you can gain control of the machine. So we will have a project coming in later where we'll practice doing this, where you exploit the machine through controlling the exception handler instead of controlling the stack or the heap. All right, so you need debuggers for this. Soft ice was once considered very powerful, but it's very old and not much use anymore. WinDebug is the main one Microsoft uses. This can debug the kernel and user land, but it has a very unpleasant interface. It's really a command line tool, very clumsily thrown into Windows, sort of like Windows 3.1 to give you a headache. It's a little hard to get used to, but it's the most powerful. For beginners, Anley Debug and Immunity Debugger are far more easy to use, nice graphic tools, and they've been used by script kiddies to cheat on Windows games for years. So they're very good for beginners to learn how to use debuggers. Anley Debug had a very nice older version. Then they tried to upgrade to a new version and messed it up so it doesn't work. Then they sort of gave up and abandoned it. So the code was sold to Immunity, and Immunity is the modern maintained debugger based on Anley Debug. So Immunity is probably the best thing to use, although in practice, Immunity and Anley Debug, the old version, are practically identical. So we'll use it a little later. You run assembly. So when you open a process in the debugger, you see the assembly code here, which is the code it's going to run. You see the registers over here, like we've seen in Linux, EAX, EBX. Here's the ESP and EBP, stack pointer and base pointer. Here's the extended instruction pointer. And there's other ones we haven't talked about much, but the top section is the main one we care about. This is the stack showing going up by 4 bytes at a time, and 32-bit words here, often pointing to addresses to things, so it can return to them. There may be other data on the stack. And here you have a pane just like the lower pane of Wireshark, where you can just dump any section of memory you want, and you'll just see the raw hexadecimal and ASCII data that's stored there. Down here at the bottom, you have the most important stuff. The bottom right tells you whether the program is running or not, and the bottom left tells you where you are. So the first thing you always look at is the bottom right to see if the program is running or not. And we'll use this in a demonstration soon. So let's do the last Kahoot. And that is here. All right. And then I'll demonstrate the project, which I recommend doing. All right. Aha, just a different name, all right. I think we still have only 2, so I'll just carry on. All right. So If you divide by 0, what happens? Use the exception handler, the structured exception handler. All right. Which debugger was good in the old version but bad in the new version? Ollie. All right. What listens on port 135? Remote procedure calls. All right. Where do you find the inputs and outputs of an object? Interface descriptor language. That's what you must write to go with your COM objects. Which one is the 32-bit value? A token, good, that specifies who is running a process. All right, which one is 128 bits long? That's the universally unique identifier. All right. And what debugger can debug the kernel? WinDebug can do it. None of the others can. And we'll do it later in the course. All right. So Alex is the only person getting points for this. And okay, let me get to the project then, which I think is very nice. And I've just got it all working. So let's go here. You go to 127, pardon me, 127, and then projects. And now we are down in the Windows section. So first you need to have Windows 2016 server. Now, originally I had this all using only cloud servers, but Microsoft seems, Google seems to have changed the rules. You can no longer make Windows servers for free. Now you can go here and get a $50 voucher, but they still give you $300 of fake money for free. But none of those seem to work for making Windows servers unless you turn on billing. And I am afraid that if you turn on billing, you will have to remember to turn it off before the free trial runs out, or they'll actually charge you, which means you can still get a Windows server for free if you're careful. But if you're sloppy and distracted like me, you might forget and leave it on and get billed for it. So I haven't done that because I make a lot of accounts and I use them up and forget about them. So I went back to using a local virtual machine for my Windows machines. And so I put that back up here the old-fashioned way where you run it in VMware. You can, of course, do that for free. And by the way, we do have VMware licenses if you want them. You can get a VMware license by going to my homepage, and up here is a VMware software. So you can put in your City College email address and get free VMware product keys. All right. So once you've got a machine running, and I've got a machine running here, let me find some way to make my virtual machine come up. Okay, there it is. Okay, this is my Windows 2016 server virtual machine. And what we're going to do is attack this Bowne server process. This is an open source vulnerable server written by somebody, and it's very nice. It's very good for practicing exploit development. So this thing is listening on port 9999, and you can connect to it. So if I open up another terminal and I find my IP address, ipconfig. Okay, my IP address is 172.16.123.248. And in the project, I have you exploiting it from a Kali machine, but I'm going to just do it from the Mac host. And I installed Metasploit on my Mac host, so I do not need another machine. So let me clear this. All right, and I'm going to clear this one, and we'll get back to these things. All right, so here, I'll make this bigger. Hopefully it will show up well on the video that comes up later. All right, so let me try and move this stuff out of the way. This I should be able to move onto the other screen. Yes, all right. So My IP address is back there. And so I should be able to connect to this machine if you do netcat to that machine, 172.16.123.248 on port 9999, if I can get my fingers to do it, 9999. Okay, then it should have told me something, 172.16.123.248. Well, that's rude. All right, let's try ping. I'm not going to get very far if my demonstration doesn't work any better than this. All right, I can ping it. That means I'm probably okay. Let's go in here. I did restart the machine. Perhaps the firewall came back on. This is, of course, a very common problem. If the firewall is back on, it'll block this unexpected stuff. And I think I did have to restart the machine. No, the firewall is off. Well, how rude. All right, let's try this. Netstat. Minus AN pipe more. It is listening on 9999 on all its TCP addresses. Let's see if I can ping out from here. This is the most common thing with my students. Okay, I have internet connection. All right, let's try IP config again. It is 123.248. All right, and it's listening on 9999. What happened? Well, that's netcat 172.16. Well, let's try IF config out here. I've got a virtual network pointing in there. Well, how rude. Oh, 123. Perhaps I hit a funny key. Netcat 172.16.123.248. Well, I just tested this right before class and it works. Now for some reason it is not working. Wait, now it did. Wait, when I closed it, it worked. All right, that is weird. Maybe it's just extremely slow or something. Let's do help. I had to hit Control-C there to make it work. Anyway, this is what you should get. Let me try exit and come back in and see if it's going to work better. Control-C. Okay, now if I come back in, 2, 3, 4. Well, I don't, now I have to click here and hit Control-C, and then I get it. Well, that is pretty screwy. I don't know if it's going to work well enough for our purposes this way. I think I'm going to stop it and try restarting it. See if that does any better. Run. Let's try it now. All right, now it's working properly. I don't know what that problem is. So this is imitating a server with a bunch of functions. If you do help, you can feed in various things with values. And the one we're going to use is trun. So if I do trun and then I give it like A, it's trun complete. And if I do trun, then I give it more, it takes that too. So at some point it's going to crash. And of course, we're going to use Python for that. So I made a fuzzer. If I cat vs fuzz, this will connect to my server on the right port. It will then ask me for length and put that in something called length. And it will then send that many A's. Trun followed by that many, a dot and that many A's. So if I run that, vs fuzz, and I feed in 100 A's, it's fine. It gave me a goodbye message. If I feed in 1,000 A's, it's fine. But if I feed in 9,000 A's, then it crashes, and you see it stopped working here. Windows has crashed, and that's what I said. It caused an exception. The program didn't handle it. It went to the operating system, and because it was in user land, the operating system was able to pop up this box and close the program. It didn't have to kill the machine entirely. So to see why it crashed, you have to run it in Debugger. So you run it in Immunity, just like we did with GDB on Linux, and then you load the program here, Vuln server, and then it shows you the assembly. When the program loads in the debugger, it is not running. The first thing you do is look in the corner down on the bottom right, and you see that it is paused. That's the most important information. You can't connect to it. You can't use it. It loads in the debugger and it automatically breaks right at the start to let you see what's going on before it runs. So here you see the assembly language instructions that are going to run. Here's the address of those assembly language instructions, and here's the raw hexadecimal bytes of those instructions. Here's the registers right now. Down here is the stack, and over here is just some part of memory being dumped out in hex and ASCII. So to start the program, I hit this go button here, run. Because it's a 32-bit program running on a 64-bit operating system, I have to run it twice. The first run just launches the Windows on Windows process, I think, and I have to hit it again a second time, and now it's actually running. It tells me running down here. So now that it's running, I should be able to send in that fuzzing again. And if I give it, say, 9,000, it crashes. And now, because it's in the debugger, instead of popping up the error message and giving me no information, it tells me what happened here. Access violation when executing 41, 41, 41, 41. And as you know from our Linux work, this is good. This means the 9,000 capital A's I put in, some of them ended up in the extended instruction pointer. And you can see it right up here on the right. EIP now contains 41, 41, 41, 41. So somewhere in those 9,000 characters is something that controlled the EIP, so we can probably take over this machine. So I hit, to get started up again, I hit debug, restart, yes, and then run again, so it's listening, and now I can send more careful attacks. And so I don't think I'll go through it in great detail. Let me point to the project instructions. So if you go here to 308, once you have a Windows machine to work with, this guides you through the process of setting up your server. And by the way, you have to lower some security settings in Windows for this project. If you just have a default Windows install, it won't work. So be sure and turn off the data execution prevention and turn off the firewall. And once you can connect, then you can run the fuzzer and see it crash. And then you just have to hit the extended instruction pointer, just like we did in Windows, in Linux. So you write a program that will feed in 3,000 characters, and you hit AAA. And then I made a Linux program that will show you a non-repeating pattern of characters here, 000A, 001A, 002A, and so on. So let me feed that one in. That was VSEIP1 is the one that sends that in. So I'll show you that one. If I go here, there's my Windows machine, and here's my Linux attacker. So VSEIP1, let's take a look at that. I guess I'll just cat it. All right, so this is the program. It just connects to the server, and then it sends it to the server and prints the results. This part will never change. All the variable stuff is here in the middle. So this has 1,000 capital A's, and then it sends 500 groups of 4 characters each, which is numbers, 3 numbers followed by A. So if I send that one, VS EIP1, then it crashes, and now instead of A's, I have 1A25 here, because 31 is the numeral 1, 41 is capital A, so it's 1A25. And if you look at the pattern of characters, you can find where a 1A25 is here. Here I got the 1A25, remember it comes in backwards, and you can look at the pattern of characters and find it, there it is. 251A, 252A, that's where 1A25 is. So from that, you can figure out how many characters there are before the extended instruction pointer, and it turns out there's 1,006 plus another 1,000 I put in there before. So to hit the EIP precisely, I need the next one, which is VSEIP2, and this one has 2006 capital A's and then BCDE. And I mentioned this before, this is where it really matters. Always put in padding so the total length of your injection remains the same. Otherwise, you will actually, in this program, you actually will hit different crashes if you forget to do that, and that will drive you mad. So make sure you always put in the same total number of characters if you want to smoothly progress towards success instead of getting derailed. And so this one, VSEIP2, should put BCDE, right in the instruction pointer. So that one has a crash, and as you can see, this is BCDE, 42, 43, 44, 45. So now I control the instruction pointer exactly. Now I just need to find some way to execute code. Let me go back to my instructions. All right, so once you control the EIP, now the next thing you need to do is make a plan of how you're going to execute memory. And it turns out that we are going to defeat address space layout randomization. Remember, that's turned on. You don't know where you are in memory. You're going to randomly move. So instead of trying to find a specific address and jump to it, we are going to just try to run code that we put right after this. So we've just hit a crash, and notice the structure of our exploit here. What this does is it sends capital A's, then B, C, D, E, and then a whole bunch of F's. That's what we injected. So let's take a look at the structure of memory here in Immunity. Here's the ESP here. And you can see there that it has F's in it. And I can follow this in the dump. Follow in dump down here, and I can see there's a lot of F's. And if I scroll up, I'll see that here's the A's, here's the B, C, D, E. Immediately after that is the F's. So there is no gap. So notice I control the instruction pointer and I control all the code right after it. So if I could jump to ESP, I would be jumping to the code I injected, which is very nice. So all I have to do is find some jump ESP instruction somewhere in memory where I know that address, and I can put that address in here. It will trampoline bounce off some function and then run the code I injected. Even though I don't know where this code is, it doesn't matter, because the ESP points to the next byte, and the next byte is under my control. This is how we defeat address space layout randomization. But we do have to find some code that is not randomized. And it turns out that Microsoft's randomization is not very complete. So if you look down here, then there's an issue of finding bad characters, which I'm going to skip over, but it is part of the project to go through and see how it works. And Mona is the module that helps you search through memory for useful artifacts. And in particular, Mona lets us see the modules. So let me show you that one. You would add Mona to your debugger, which you do just by downloading and putting in a certain folder, because the debugger is a framework and you can add more Python code to it. And then I put in bang Mona modules. This will scan memory and find out what modules are loaded in memory. And the cool thing about this is it will show me, let me make my window a little bigger. The easiest way to see what's missing. Okay, so here's the modules loaded by my function. Here's Bowne server itself. Here's a DIL called ESS func, and here's other DILs like kernel and MSV CRT. And the point of this Mona tool is it finds out all the modules and it tells you what security is turned on. So notice, here's address space layout randomization. Most of them are randomized, but 2 of them are not randomized. And here is rebasing, which we talked about in the lecture, which also can move things. And it turns out that those 2 modules also don't have rebasing turned on. So these 2 modules never move. Now, this module is Bowne server itself. And that might be nice to use, but the problem is it's loaded too low in memory. Remember, we said executable files always think they are at 400,000. That means the first byte of every 32-bit word always is null. And we can't inject a string full of nulls. So even though this is full of code that doesn't move, we can't use any of it in our attack because all the addresses will contain null bytes. But this one, ESS func, is the winner. ESS func has the defenses turned off because it's old code, and it's loaded at a memory location that doesn't have any zeros in it. There's a lot of addresses in that function that we can use. So all we have to do is find a jump ESP in there. So there are various ways to do it, and later versions of Mona have more convenient ways to do it. But this works if we can look for particular hexadecimal codes. So you can use a assembler in any program, or even just look it up on Google and find out what pop ESP and return is one way to do it. Jump ESP is another. It turns out jump ESP is good enough. It's a fairly common machine language instruction. So if I can find FFE4 anywhere, I can use it. And this is how you look for FFE4 in Mona. Find the sequence of bytes FFE4 in the module ESSfunc.dil. So if we run this, Mona will find the code we want in the module that is vulnerable. So it finds 6 or 8 of them here. These are places where that appears. We can use any of these. And the only remaining consideration is we don't want an address that contains a null byte. And as you can see, none of these addresses contain null bytes. So there's 9 pointers. We could use any of them. I just used the first one. So this is the code to jump to, 6250 11AF. And I think I'm not going to demonstrate it all live anymore. I think you probably are getting the idea. So now all you have to do is put in that address, 6250 11AF, and then you put in a NOP sled and then some breaks. And that's a way to test to make sure it's going to work. And it will execute because we turned off data execution prevention. So we can't execute code on the stack. So that one will show that code execution works. And you can see it if you send that one in, because it will slide down the NOP sledge and hit 46, which is the F. All right, and I have a little trouble scrolling here. All right, and so you can see it slid down the NOP sled. Anyway, then the final attack code is over here. Let me just bring up my demonstration. All right, so Control C. That is VS Shell. All right, so here, all I've got, I would like to scroll, here we are, is at the start, I just have the generic stuff that connects to my server. Here's what I have, 2006 AIDS, then that address that came from Mona, and now I just have stuff that comes from Metasploit. I put in a 16-byte NOP sled, and then I just created this in Metasploit as before. It will phone home to my command and control server. And then down here, I just pad it to 3000 and send it to the server. So if I start a listener over here, this should work. If I start MSF console here, and I authorize myself as an administrator, then I have to start a listener with, here's, by the way, the meterpreter command to make reverse shell with my command and control center IP address here, which in my case is my Mac host. And so to start a listener, I use these commands to start listening on port 443. So that is here. I paste in that stuff. All right, so now it's listening on port 443. And so if I make sure this process is ready, it's paused right now. So I have to do debug, restart, and yes. And that loads it, but it's still paused. I have to run and run again. Now it's running. And now I should be able to go here and run VS shell. And I'm going to shove this over to the side so you can see the results. Here's my listener. There's my debugger. So I send that. And you see down here, it's still running. It didn't crash. It's loading DILs and starting some thread. And here it is opening a interpreter shell. So I can do like sysinfo and get UID. And I am now running as administrator because this machine is logged in as administrator. So I now have control of that machine. And so you should try it out. This is the most important project in the course if you want to get OSCP certification. As one of my students told me that. This is pretty much what you have to learn, how to take over Windows servers over the network. And then you can practice against a real remote server. Since this is open source code, I modified it a little bit and recompiled it and made a modified version of this thing called Vuln4T, so you can't use exactly the same exploit. You have to develop a new one, which is a minor variation on it, and you have to work from a real cloud server that's connected to the real internet. You can't be behind network address translation because your command and control center has to be available to the target. So you can download a binary here and run it locally until you develop your exploit. and then you can take over my server and find a flag on there. So check it out. It is very much worth your time. This is the heart of Windows exploitation, and all future projects on Windows will be variations on this starting point. So that's what I wanted to show you, and see if anybody has any questions. I haven't got very many students, so I see something coming up here. We're still welcome to use VMs. Yes, you can use VirtualBox or VMware if you want to, and that's what I did because I didn't want to take the chance of having to pay for Google. Yeah, good. You can use, because the only point of you running your own Windows is just to practice. Then you exploit a real server, you have to use a real cloud server for that. But you can get a free Google Cloud server, or you could in fact work from home if you have like a Comcast connection and you put your home machine in the DMZ part of the firewall so it's really exposed to the internet. But you know, the simplest thing is just use a cloud machine. Are there any more questions? All right, well, I'm thinking there aren't. So I will stop the recording and then I'll stop the share pretty soon.